I guess a lot of participants are running late today. We can get started now. Actually, it's already time. Just want to do a quick recap of what we did yesterday, and we shall continue with today's topic. So first of all, if I go back to the day 3 tab, uh, we briefly try to understand like how project is initiated. So starting from the CTQ finalization, then getting your team in place, and then finally your project charter. The elements of project charter is what we discussed. Uh, After that, again, pretty much you look into the selection of team. The GIP tool is what we discussed. The communication plan, uh, and then the RACI or RASIC chart, which is what will sort of complete your define phase. There's one tool which is left here. It is going to be used when we are going with the DFSS method. If you remember, we talked about DFSS where we said like first you do a VOC collection, then you take it to quality function deployment. So this is the QFD actually we're talking about. So we're parking this for later stage. Why? Because when we are doing design of experiment, that is when we will be discussing this. So this is something which we are parking. So if you remember the sequence, when we're creating a new product or a new service, new process design, in case of DFSS, first of all, we start with a VOC, voice of customer needs to be collected, which will further be taken to quality function deployment to select what is that we can work upon. And from there, we take it to FMEA. We already covered FMEA yesterday. And once we have secured the metric that we want to improve, that's when we take it to DOE, design of experiment. So technically we have to cover up this QFD and then the DOE part, which we will cover up later, because when you do the design of experiment, we shall discuss the prerequisite of it, and that's when we'll cover it up. But that'll happen towards the later part of the entire program, because DOE is a complex part. But before we get to the DOE, we'll take up QFD. So it will make sense when we're doing a DOE. So pretty much with what we covered till yesterday, we have sort of finalized the define phase. So define phase is more about selection of the project, selection of the team, planning with the team as to how the project will be executed in terms of your communication plan, in terms of your roles and responsibility delegation. The team is ready. Now you want to officially start your project. Now, in case of when we get into the measure phase, but before we talk about measure phase, there is one thing I would like to request everyone to fill in whenever you get time. So this is some mock test which we have. So for every phase, whenever you're done with the phase, you can go and appear for this mock test. It'll give you a fair bit of idea how the questions can come from a different phase, and it'll be a quick check. So uh, I need to assign rights to everyone on this one. For that, I would request you to please fill in this particular uh, Excel sheet, which is this mock test details. I need the Google IDs, the Gmail IDs. So just mention your name and the Gmail ID. I will be able to assign rights on this to everyone. So pretty much whenever you like, not right now, but whenever you get time, please do update your Google Gmail IDs here. So I will be able to kind of get the access to everyone. You get an email with a link to appear for these exams. So whenever we complete a particular phase, you just go to that respective tab and then appear for that exam. There'll be additional things which will be adding on from a black belt perspective, which will be added on to this one, because most of the questions here are from the green belt perspective, which is a portion of black belt also, but plus the topics which are different from green belt and specifically are very, very specific to the black belt, that will be a separate thing which will be added on. So please do fill in this sheet whenever it's in the same Google Drive where we put the notes, where we save the notes. So please access this whenever you get time, right now, later, whenever you want to do it. do fill in this details here. So by when I'm done with the session, most likely by tomorrow morning, I guess even like before yesterday's session, I said tomorrow's session, I will be able to kind of make sure that I will go and assign all the rights to people who have filled in this. So you can try out define phase test and get to understand where you are, like if you're confident enough to kind of understand every question there. If there is some certain things which you feel, no, I still need clarity, at least there'll be a quick check. So please do take your time to kind of fill in this. So I'm just crossing it off. uh, this is the sheet which says mock test details. It is in the same Google Drive. Just uh, get it done like so. This is the same Google Drive. Just fill in this details sheet. That,
Um,
yeah.
I actually tried it, but it shows here that it's only view. So I
Okay.
tried to request an access.
Okay. Okay. Give me then one quick second. I will change the mode. Mm-mm-mm. Change to anyone. I guess that should uh, take care of it.
Okay, thanks.
Perfect. I guess it should be fine for now, everyone. Just try it out. You should be able to make changes there.
Can you please share the link, Google Drive link on the
Yeah,
chat,
yeah, yes, yes. Same
WhatsApp group?
group. Yes, I'll share the Google Drive link on the WhatsApp group. I'll do that. Like so, it's by the way, it's there in the Excel sheet notes. Like the same. This is
Okay,
where
okay.
this is the link. Same link where we place the notes. Every time when we place the notes, it's in the same Google Drive link. So within that Google Drive, there's one file that I have just placed, which is mock test details. Just fill in these details, and it just needs the email ID. Technically, I just need the Gmail IDs. Well, Victor, I guess there's some typo. Just work on it whenever you get time, and by post today's session, I'll just go and check it out. Whoever has have filled in, I'll get it done. So that way, we'll be able to take care of it. Let's move on. So now, pretty much from define phase perspective, we have kind of covered it. So we know the tools and techniques which are required in define phase, the flow of a project in define phase. We are aware of it. Now we get into the measure phase. Uh, Having said that, we still have certain things which we have parked in the define phase. We already talked about those things which we will cover later on, which I do still remember. So we will cover them up because they're different project prioritization models and stuff like that we discussed on the, I guess that was day 2. Yes, we are going to cover up. So this QFD is something which is pending. We will be talking about that along with this DOE. We left with these, which we will be covering in the improve phase. So certain things are there which will come in due course of time. So we'll park this for now and we'll move on because this is a separate, like this will generally go with DOE, which is a separate stuff. Won't not be a general part of your DMAIC process, but yeah, you can still use it. These are just tools. Starting with your measure phase now. Measure phase, your management has already approved the project. You've got your team. Now, the first thing, the purpose of your measure phase. Anyone wants to share what is the purpose of measure phase? What do we do in measure phase?
We measure uh, the depth of problem. We measure your data, what we have, and
Yes.
we validate all the data and make sure which level of we want to do our the like
The improvement.
improvement. Yes.
Okay. All right.
So basically, we do the baselining during the measure phase,
Yes.
and
Yes.
post baselining, we also will try to look into, as the colleague told, we look into whether we have all the relevant data
Mm-hmm.
which is necessary for doing the analysis, and
Absolutely.
also to look into what is the depth of the improvement opportunities available, so that we can focus on that particular piece. And also we will look into the data, whether it is a discrete or continuous. All those things will come in measure phase.
Perfect. You are absolutely correct. So Yes. So my entire purpose, see, Six Sigma is data-driven study. So data needs to be collected, which will be analyzed. So every phase, the analyze phase is about analysis. So before an analysis, you must have the data. So data will be collected in the measure phase, which must be reliable. So that brings us to the measure phase. Before we start discussing about everything here in the measure phase, what is that we do? We will be briefly talking about some basic statistics stuff. We don't need to become statisticians here at this stage. In Six Sigma professionals, we are not statisticians, but yeah, we are users of statistics. We use stats to take decisions, to make business decisions. So yes, none of us never intended to become like, if you really want to become statistician, you want to go in detail, in depth, yeah, honestly, we need to spend good 6 months, at least 6 months, when you're studying every day. So that will, you have to pick up a hard book, when you have to diligently pick up statistics from core. That will be a lengthy stuff, but thanks, we have softwares now like Minitab, which takes care of all those issues. But yeah, if you want to do it, nothing wrong in it. You can definitely try and explore in-depth statistics. Yes, you can definitely try that out. But yeah, from a Six Sigma perspective, whatever is applicable, we will be trying to go ahead with this. So first of all, before we get going with the things we cover in measure phase, let's understand the data part. Data, or how data can be classified. So first thing first, we would like to understand the data types, how data can be classified for the different types of data. Now, definitely need your input here. What are the different types of data?
Uh,
What?
Continuous and discrete.
Continuous and discrete.
Discrete
Attribute.
data.
Okay, perfect. Continuous and discrete. So continuous is also known as variable data, and discrete is also known as attribute data. Now, help me understand, what is a continuous data?
date date range
Which
is
has
in
a
the continuous
measurement
data.
unit against it, which can be
Yes.
measured.
Okay, perfect. That's the correct one. Yes, a data which can be measured. Which can be measured is your continuous data. Simple as that. Any data which can be measured is a continuous data. When I'm saying it can be measured, bottom line, it must have a measurement unit. If you don't have a measurement unit, that means you cannot measure it. So any data which has a measurement unit, what kind of data, like weight, height, volume, anything which we can measure, like time, it has a measurement unit. Can I measure the weight? Yeah, I can measure this in kilograms, grams, milligrams, tons, quintals, like pretty much there are a lot of units. Height, I can do it in inches, centimeters, millimeters, and so on and so forth. Feet, foot, and stuff like that. Pretty much a lot. Volume, I can still measure in liters, and like a lot of options are available. Time, we can do it in hours, seconds, pretty much minutes. This is the beauty of continuous data, that it has a lot of units, a lot of ways I can assess this. Like temperature, I can measure in Kelvin, Fahrenheit. I can do it in degrees Celsius. Anything which has a measurement unit is a continuous data. Simplest way to find what is a continuous data, just ask yourself a question. Can I measure this data? Yes. Then there's no question asked. That is a continuous data. Now, other than this, continuous data has a couple of more properties which we should be aware of, because that will help us ensure there's no ambiguity left in terms of having an understanding between continuous and discrete. So continuous data is best quality data, and as you need minimum data for analysis, very less data for analysis. Let's take a simple example here. Say I've been talking about this same example for so many years now. My weight is 70 kilograms. My friend's weight is also 70 kilograms. Does it mean we are exactly the same? Technically not. I can go to next place of decimal. My weight is 70.3. My friend's weight is fortunately 70.3 also. Can I further extend this? Yes, why not? I can go to next place of decimal, say this is my weight, and this is where this is my friend's weight, and I know my friend is little heavier than me. So the beauty of continuous data is that I can stretch this till infinity till I find which one is a bigger number, which one is a smaller number. I need less data for analysis. Why best quality? Because cost comes into picture. More the data, more costly will be the project. So practically for analyzing a continuous data, you don't need too much because it can be stretched till infinity. It's a best quality data. Project cost will be least. So if at all ever you have a choice and you are the one who's deciding on a project, don't try to be saint. It's yeah. Don't we do a project on discrete? Yes, we do discrete projects also. But if you are the one who's deciding it, always prefer continuous data. Why? Because project cost will be less. You will be able to finish the project sooner. You'll be able to prove something sooner as compared to discrete data. It will be time consuming. It will be difficult to prove something in a discrete data, and we'll understand why. So, by bottom line, this is the first choice data for any Six Sigma professional. It's see, we do not want to prove a point that we can take up a tough project. Sorry, it's not about how tough project this is. No, it's all about the number of projects you are able to complete. That's what brings you to the limelight. Practically, that's what matters. So the turnaround time for a continuous data project will be very less. It helps. It's a good thing to kind of keep in mind from a real world perspective. And other than this, it can be interchanged, and it does not change its original meaning. 1 hour is equal to 60 minutes is equal to 3600 seconds. The definition, the meaning has not changed at all. I can convert dollar into pound, in rupee, and dirham, dinar, doesn't matter. In euro, it is interchangeable. Thanks, you have multiple units. These properties are available with continuous data only. You will not have the luxury of interchanging in case of discrete data. So we'll understand the limitations as we discuss about discrete. First thing first, what is a discrete data? Simple as that, which is not continuous. Something which is not continuous, that means you will not have a measurement unit, will be a discrete data. Well, that is of five types. We have binary, we have ordinal, we have nominal, we have count, and we have percentages. Now, the last one is very much debatable. Across the globe, people are divided into two blocks. Some say percentage is a continuous data, and some say it's discrete data. I'm one of those who says it's discrete for valid reasons. I have my own perspective. Yeah, a lot of people have uh, do believe and argue about the fact that percentage should be a continuous data. Technically, it's very close to continuous, but well, my perspective says it's still a discrete, and there is a reason for it, which I'll be able to share right away. But the second best quality data is your percentage data, which is in number format. Third best is this one. Fourth best could be these two, it doesn't matter. The worst data that you should avoid to work on is this one, binary. Worst data. Refrain from it. Well, let's understand binary. Now, binary data is the data which can contain only two values, like yes, no, pass, fail, true, false, 1, 0, just two values, AM, PM, male, female, only two values. Worst quality data. Now, just think about a situation where I have a criteria where I say more than 90% is pass, equal, less than or equal to 90% is fail. Well, uh, if somebody scores 90% and somebody scores 0%, both will be tagged as fail. Only if I score 91 is when I am being tagged as pass. So much of chaos here. 90 and 91 is just right next to each other. And see, this 90 and 90 and 0% have no differentiation. Even 0 is fail and 90 is also fail. Sorry, it doesn't give you clear picture when I'm looking at pass or fail. It doesn't tell me, is this fail 90, 89, 85, or 0, 1, 2, 3. It's too bad. So much of ambiguity. When you calculate sample size, we'll go about learning about the sample size part of it. We will see that this is the sample size in discrete data is huge, because to prove your point, you need a lot of data, because this doesn't tell you the complete picture, doesn't tell you pass or fail. But if it would have been these numbers, like if there's somebody score passing marks are like this, say 87, 88, 89, 12, 34, 98, 95, 91. Well, this is fail, 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 this is pass, this is pass, and this is pass. It looks like I'm doing so bad. Technically, am I that bad? No, these were very close to being passed, but it looks like horrible, like this 12 and 34. They're more like these numbers. Well, that's why there is a lot of data which is required to prove your point. In this case, it's the worst data. You should refrain, if you get a chance, always refrain from a binary data. Your project cost will be very high. Ordinal data, well, if it's more than two, if it's two, then it's binary. If it is more than two, then it is ordinal or nominal. Now, what is the difference between ordinal and nominal? How will we understand if it is an ordinal data or nominal data? First of all, like data which has a logical sequence, order is continuous, is a ordinal data. Technically, ranking, rating data is your ordinal data, like rating of 1, 2, 3, 4, 5. These are not numbers. They represent a position. I can't say rating of 1 plus rating of 2 is equal to rating of 3. Sorry, no, that doesn't mean. These are not numbers. These are not number 1 and number 2. They represent a position. There is a meaning for every value. You can't just add up these values and say, this is like going to be 1 plus 2 is 3. Sorry, that doesn't work that way. Or rating of 1 plus rating of 4 is equal to rating of 5. No, that doesn't mean. Similarly, we can say excellent, good, average, bad. Well, that's a logical sequence. There is like a sequence in it. There's a ranking in it. There is a sense here. So this kind of data is your ordinal data, which has a logical sequence, some sort of ranking in it. Normal data, no ranking, no order, just name. Like I can say Reebok, Adidas, Puma, Nike. Well, does it tell me which one is good or bad? No. Can I bring Nike in the beginning, take Reebok in the end? Absolutely. Go and do that. What's it doesn't tell me anything. Just a name, just a label. I can say like blue, green, yellow. Well, does it tell me anything? No. Just a label. Manager one, manager two, manager three. Doesn't tell me who's good or who's bad. But ordinal data does tell me something, some position. It's just a label. Count is basically everything which can be counted, like it's self-explanatory. Errors number of errors, uh, number of parts manufactured. uh, you can parts manufactured, like, and you can say mm, like number of invoices processed, or probably the number of insurance claim process, stuff like that. Anything which can be counted. Remember, this will always be whole numbers. You cannot process, say 34.2523 invoices. No, that cannot happen. Either you'll have 34 invoices or you'll have 35 invoices. You will always have whole numbers. They cannot go in fraction. These will be absolute whole numbers. The percentage one was definitely the percentage, like we can explain in quality percentage, defect percentage, humidity percentage, anything which can be expressed in percentage. Closest one, why? Because can I write percentage like this? Can a percentage be like this? Why not? Percentages can behave like continuous data. They can go till infinity. We can extend this fraction till infinity. And yes, it has this property of continuous data, which can be stretched. The only problem here is that it cannot be interchanged. I cannot convert. This is out of 100%, out of 100. It doesn't have a measurement unit. I cannot interchange, and that's why percentage, even though it can be, it has a lot of properties of continuous data, it cannot be treated as a continuous data. Why? Because it cannot be interchanged. You cannot roll up, roll down practically. There's no unit in which you can convert this. It is the drawback why percentage still has to be a discrete data and not a continuous data. So that's more about the types of data. Now, just quickly want to check with every one of you, like, are we okay with this? Are we clear about what are the different types of data?
Yes.
Yes.
A quick question now. I like so we are developing a new car, and currently my car has mileage. It gives me a mileage of 25 kilometers per liter, and we would like to make a new car which will give me 30 kilometers per liter. What kind of data is this?
Discrete.
Continuous.
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 It is continuous, and
Discrete.
it is continuous data. Why it is a continuous data?
It's
Because kilometer,
interchangeable.
Okay, fine.
kilometer, and this is per liter. Kilometer, is it continuous? Yes. Is liter continuous? Yes. Is it measurement unit? Yes. Both are measurement unit. If I talk about, if I'm developing like if I'm looking at the speed of the car, currently we have like 100 kilometers per liter, so per hour is the speed. We would like to make it like make a car for which will give me 125 kilometers per hour.
Continuous.
Again, a continuous one. We have got this as continuous data as a whole unit. I am trying to improve the productivity for an insurance claim process, and we have been processing like 500 claims per day, and we would do, if we do a project, we would like to improve it to 750 claims per day. What kind of data is this?
Discrete.
This counts, right? So in
Discrete.
Count data.
discrete data.
Absolutely, yes, 100% it's count. Now, in order to achieve this, I believe, and as a group of individuals, we sit down, brainstorm, and we figured out that it's an insurance claim process. People are working in the back office, they are typing something, and their typing speed is very bad. Like currently, we saw that on an average, we have like a typing speed of 25 words per minute. And if we increase the typing speed with the same manpower, we will be able to achieve this 750. If we increase it to 40 words per minute, uh, I would like to, I would be able to increase my productivity because people will type faster, will be able to increase the productivity. What kind of data is this?
Discrete.
Discrete.
Anyone has any other perspective?
It's actually comes in nominal, like in words. So you said that
Count,
words
this is count. Like why this is
25 and 40.
25 words were per minute, count of words per minute. Now there could be a question like per minute. Minute is continuous. Yes, minute is continuous. But the words are, so the reason why I was trying to take you to this level, why? Because whenever there is a single unit like this, like we talk about time, day, anything which what we discussed, it's easy to understand. But whenever there's a combination like kilometer per liter, kilometer per hour, claims per day, words per minute, the confusion will arise there as what will be the overall unit. The thumb rule, remember this, if you have continuous divided by continuous, it is the overall unit will be continuous.
Okay.
That's the only condition where it will be continuous, like this one, kilometer per liter, kilometer per hour. Continuous by continuous will be continuous, the overall unit. Everything else will be discrete, like continuous divided by discrete will be a discrete. uh, Discrete divided by continuous will be discrete, and discrete divided by discrete will be a discrete. Whatever forms you may look at, you will always have it as the overall unit will be discrete. The only condition where the overall unit will be treated as continuous when it's continuous by continuous. Like here, it was count of words, which was discrete, divided by minutes. Minutes, which was continuous. Discrete by continuous was discrete. The overall unit, because Can I type 25.354 words per minute? Sorry, no, I cannot. It has to be count. So continuous means I can bring that into fractions. Can I do that? No. Either I will type 25 words or 26 words. Continuous can always be broken down. This cannot be done. So it's simply a count. That's why. That's the logic. So remember the thumb rule. If you have continuous by continuous, that's the overall unit is continuous. Rest everything will always be discrete version. I hope we are good with this.
Shashi, can you just say this example continuous divided by continuous? So you are saying 25 kilometers by liter.
Yeah, kilometer is a continuous data.
Yeah,
Can I
and it is
and
also
liter is a
continuous.
continuous? Yes, that's why continuous by continuous will be overall unit will be continuous.
Got it, got it. Yeah,
Okay,
thank you.
all right, perfect. Now, once we have got the idea of the type of data, the next thing we have to understand is when we are going to get the data, what kind of analysis will we be performing in the data? Data analysis is what we'll be looking at. Now, very basic stuff. We just trying to go, I will just go through the slides just to kind of make sure we understand some bit of basic stuff. All right. Okay. There are two students, and we would like to understand which one is a better student. And trust, there is no catch here. Very simple, basic answer. Which student is a better student, and why is it a better? Like why the person is a better student?
Student A.
Student A is a well.
Yeah,
You are 100% correct. Yes, student A is the better student. Why?
the marks secured
Because
is
the marks, it's there is no big variance in the marks.
Okay, perfect. So what else can you like what how would you generally compare two data sets? We're comparing these two people, these two students'
Student
marks.
A got all above 70 and
Mhm.
student B got less than 70 also.
Perfect. What else can you?
And
Fluctuation of
one we can give range also, student A have range from 70 to 95, and student B is having a range from 45 to 99.
I think the coefficient of variation
Right.
is the student A lesser CV compared to student B.
yeah.
Yes. And how?
Even average, if you just take the average also,
Yeah,
student A will be better than
absolutely.
B.
Absolutely, yes, without any doubt. So you answers, all of you had correct answers. So without, so as I said, there's no catch to it. Yes, technically, when we talk about data analysis, the first thumb rule, everyone in general, we look at central tendency of the data. We always look at central value of data. Where is the center of the data? Now, when we talk about central tendency, the first way how we measure in reality, in traditional world, in general, we look at averages. That's what we talk about, average. We look at mean of the data. Now, how do we calculate mean? I'm just going to use a very simple data set for a specific purpose, just to make sure that we understand the basic purpose of mean. Like everyone knows how to calculate mean, but for a specific purpose, I'm trying to redo this just to kind of like it will be repeated somewhere. 2, 5, 7, 9, and 12. We've got a small data set. I want to find the average of this data set. Well, how do I find it? Like it's sum of all the values divided by count of all values, and that's what gives me the average. So let me just quickly try and do this. Say sum of these values is 35, count of these values is 5, and my average will be sum divided by count. And that's what we do in traditional. We know average. Now, when I look at average, I know it's 7. Well, it looks like a center of the data. Central tendency, when you look at average is the center of the data. It's representing the center of the data. Well, that's what it means. It looks fine. There's no problem with this average. And we all know the formula. So average, we all know how to do it. So we can directly find the average formula and get these values. So there's no hassle. This is absolutely fine. What if I have another data set which looks like this? 2, 5, 7, 9, 250. Now, let me directly find the average here. Are you okay with this average? Should I be
No.
looking at this? No,
No.
absolutely.
No,
Here we should get the median.
Yes,
So the
thanks.
250 is on a very higher range.
Absolutely, yes. So this data, this data, 7 looked like an absolute center of the data. It represented the data. This 54.6 is nowhere representing the data. Is it the center of the data? No ways. Just because of an exceptionally high value, my center has shifted, and it's not a right metric. So rightly pointed out, yes, we cannot never. So this kind of data that we're talking about, this kind of data is called a normal data. Normal data. Normal data, we always use mean. Whenever data is normal, we always use mean. But when the data is non-normal, so for non-normal data, it's not normal, it's non-normal data, never use mean, because mean will be uh, highly influenced by the outlier value. What we use is median. Median is the right metric for non-normal data. Now let's understand how median works. I'm sure we all know it, but sort of a quick check. Whenever we are working on median, if you're solving median by hand on a piece of paper, how median will be calculated, how it will be done. First of all, data is sorted from either in ascending or descending, whatever ascending or descending format, whatever works best for you. You need to sort the data. In our case, the data is already sorted. Now, in Excel, you don't have even have to sort the data. Sorting happens in the backend, so you don't need to sort it. It works fine. But if you're doing it by hand, then you have to sort the data first. Once you've sorted, the formula is n plus 1 divided by 2. That will give you the position of the median. Where is the median? Position of median. Let's quickly understand what is n. N is the total values here. 1, 2, 3, 4, 5. There are 5 values. 5 plus 1 is 6. 6 divided by 2 is 3. So I'll just write it this way so that we can have these values separately. 6 plus 1 divided by 2, that gives me 3. So 3 is the position of median. Where is 3? 1, 2, and 3. Either you go from the top or you go from the bottom, 1, 2, and 3. So you will find your median. So this 3, here we get 7 is the median. 3 tells you the position. Where is the median? The position of the median is the third position. That's what it tells you. Now, the property of median is what we have to keep in mind. Median is, it divides the data uh, from the center into 2 equal half.
I'm
It
sorry.
is, yes,
The n here should be 5, not 6.
my
right?
bad, my bad, my bad. Yes, you are correct. Absolutely. Yes, you are correct. So uh, it divides data into 2 equal halves. Median, so half of the data is less than the median, and remaining half is more than the median. Always, median is right in the center of the data. Half data will be less than the median, half data will be more than the median. Median is always right in the center. So it is the 50th percent value in the data set. That's what you got to keep in mind. Now, this was for a odd data set. If we have an even data set, the simple like 2, 5, 7, 9, 12, and now we got 250 here. Now, in case of an even data set, same logic will be applied here. Okay, n plus 1 by 2. N plus 1 by 2, n is equal to 6 data points. 6 plus 1 is 7. So 6 plus 1 is 7. 7 divided by 2 will give me 3.5. So 3.5 is the position of median. Now, where is 3.5? 1, 2, 3. This is third position, and this is fourth position. So between 3 and 4 will be 3.5. So what we'll do, we'll take average of 7 and 9, which will give me the median. So average of 7 and 9 is 8. 8 is the median of the data. Now you can see 8 is not even present in the data. You don't have 8 in the data, but 8 is the median. because between 3 and the position which is 3.5 will be between 3 and 4 position, the third position and the fourth position. The average of it will give me 8, which is 8 is the median. Does it fit in the logic? Yes. Half data is less than the median, the 3 data points, 257, 3 data point, and half data is more than the median. 8 is at the center. So this data is not even present in this, but median is 8. Let's solve it using the formula. Median for the first data, 7. Median for the second data, 8. So this was the manual way. Technically, we can solve it by using the direct median formula also. So are we all okay with this median, everyone?
Yeah.
Yes.
Okay. Now,
If it's not in ascending, I mean, if it's not in ascending or descending order, will the formula still be the same if we apply it in Excel?
Absolutely, yes. It doesn't matter. Excel, it happened. The sorting happens in the backend, so it doesn't matter. Like pretty much, it can be up and down. Doesn't matter. Still, you can do manually. Like right now, you can use them. You can sort it and still get it the same value. I can directly use median. It doesn't matter. Excel, you don't have to do anything. It will give you the correct, because sorting happens in the backend. They will do backend. The sorting and the n plus 1 by 2 is happening in the backend. You will still get 36.
But our median formula is n plus 1 by 2. So here
Yeah,
also
manually we are not like, so when you're doing manually, then you have to sort it and do all that stuff. Excel, you don't have to do that, because this
correct.
is happening in the backend. The sorting is happening, but it's happening in the backend to give you the answer. Are we good with this, everyone?
Can this be
Yep.
done for both types of data, discrete and variable?
Yes, anything. It doesn't, it
Okay.
has to be numerical data set.
Okay.
And having said that, now this is a small data set. We were easily able to spot 250. We know it's a non-normal data. Well, what happens when there's a huge data set? Say we're dealing with 100 values, or we're dealing with 1,000 values, or we're dealing with 10,000 values, or probably for that matter, million data set. Well, how would we identify if the data is normal or not? It's humanly not possible for me to go and check every single data set and see, is it very high or is it very low, and what will be the definition of a very high value or a very low value. So that brings us some bit of uncertainty as to, but bottom line, we got to keep one thing in mind. If data is normal, we are going to look at mean. If the data is non-normal, we'll never look at mean. We'll always look at median. So thanks for that. We've got this tools available. I will be placing like a file, uh, an Excel file, which will help you solve this. Right now, let's kind of let me quickly do this on an Excel sheet right now on this 1 minute tab. Just want to create a sample data set, some random sample, just to kind of give you an idea how do we check if it's a huge data set. So I am creating, say, 1,000 samples, and we'll store it under sample head with an average of, say, 50 value and a standard deviation of 5, some random data. I'm just creating any random. I could have typed it in Excel, copy pasted there. I don't know if the data is normal, non-normal. I have no idea. How do I check it? Anyone would like to pitch in? How do we check for data if it's...
We do the normality test.
Yes. What test?
I forgot.
The answer is correct.
Anderson-Darling normality test.
Yes, absolutely, yes. Anderson-Darling normality test is what we will perform. And if you get the p-value less
Less
than
than
0.05, what does that mean?
non-normal data.
Absolutely, the data is non-normal. And then you have to look at median. If your p-value is equal or more than 0.05, your data is normal, and you should continue with your mean of the data. Now, I will be like, there is a lot of limitation on Excel, but like wherever I can provide certain templates which can help you do this, I will do that. So I will be placing an Excel sheet wherein you can paste your data and it will perform the test of Anderson-Darling for you. So where we don't have access to Minitab, again, so there's not anything for everything. We cannot have Excel version. Sorry, Excel is still getting updated. I'll try to ensure that I can cover as many things as we can on Excel, just to keep in mind, like it's accessible to everyone. But yeah, we have a limitation on Excel. So, but yeah, for this one, I will definitely place a template, the which has that feature. It has the formulas baked in. So pretty much you just need to paste your data, you get your p-value. So I'll place this Excel uh, normality test. So Excel normality test calculator, whatever, test calculator, the AD calculator. I'll place it in the Google Drive, which you can download. So this can be utilized by everyone in every industry if you don't have access to the mini tab in your organization. Say some random data. I will check stats, basic statistics, and I go to, there's two options I can look for. Either I go to graphical summary or I go to normality test. So I'll first check for normality test and then I'll go to graphical summary. So normality test, I select this sample and here it says test for normality. It gives me the option as Kolmogorov Smirnov, the oldest version, which I would say the better version or latest, like I would say it was sort of, I won't say like this was a better version than definitely Ryan Joyner. They came up with a better version, more robust version of finding normality. I'm not saying this is obsolete, but Ryan Joyner's version was better than the Kolmogorov version. During the same time, Shapiro-Wilk also introduced a method of calculating the normality, which was similar to Ryan Joyner. Both became popular, but the latest one, the most advanced method of checking normality is Anderson-Darling. So Minitab will always put things in an order. The most advanced will be always on top. The oldest one will be at the bottom. And the most advanced will be always selected by default. So we never change this. It's as it is. Click OK. So that's what it looks like. This red line is my best fit line and the blue dots are my data points. The simple thumb rule says if my data points are on the line or very close to the line, my data will be normal. At times, images may not still give you a clarity because it sort of gets difficult to understand how far is okay. So that's when we have to have a p-value. Now, p-value here in this case is 0.061, which means the data is normal and I should be looking at the mean of the data. P-value 0.061. If it's less than 0.05, it's non-normal. Is it? No. This data is a normal data. I hope everyone is okay with this. Is anyone there who's not clear about it? Anderson-Darling normality test. It's the testing, how we check the normality. Joanna, is it okay?
Shashi.
Yes.
Yeah, just a quick question. So
Mhm.
if the data, if the data is not normal, the
Mhm.
p-value is less
Less
than
than
0.05. That it means
correct.
that you need to use the median as a measure of
Absolutely yes.
central tendency.
100% yes.
All right.
Absolutely.
All right. Yeah.
We will see. We need to have the clarity as to
Mhm.
what should we be looking at when I'm looking at data. Should I be looking at average of the data or should I be looking at the median of the data? For that, I need to know data is normal or non-normal. So basis this,
Yeah.
I know the data is normal, so I'll continue with my mean.
Yeah. I think this is very important because
Yes,
in industry they usually use mean most of the
yes,
time without even looking at if
absolutely.
it's normal or not.
Absolutely, yes,
Thank you.
absolutely. Thanks. Uh, Joanna, no, this is not Minitab's terminology. This is statistics. So even if you like, as I said, there's a Excel template I will be sharing, which you can use for testing normality because there are organizations where we don't have Minitab access. So yes, you can still have those Excel templates and can use your data on that template to check for normality. So this is standard. Like I said, it's a statistics. It's everywhere, not just Minitab. Minitab makes it easy. Okay, let's then check the other version. Ideally, we don't end up using this version for checking normality. We end up checking the other version. Like this is okay, but everyone prefers this other version because that gives me complete information. Every possible analysis about this data can be done using stats, basic statistics, and graphical summary. When I click on this graphical summary, I select the data sample. I double click this, it comes here. I click OK. This is every possible analysis that I need to know about this data. It is absolutely fine. So we are going, Joanna, with a perspective that you like. There could be participants who have not done the green belt. So we are going from the scratch. So that's absolutely fine. Please don't hesitate. Again, this is how it has to be. So we'll cover up everything from the scratch. Okay, perfect. So now we are looking at this p-value here. So we'll come back to all this information one by one. For now, I guess this is complete analysis about this data, and a lot of stuff we need to come back and check. For now, we are just checking the normality. Anderson-Darling normality test. By default, it's picked up. Same p-value. Why we do this graphical summary instead of the other one? Because if the data is normal, like let's have a quick look at it. If the data is normal, what should the data is normal? Look at p-value. Yes, it is normal data. I should be looking at mean, the average of the data. What if this data would have been non-normal? Then I don't have to do it anything else. The median is already there. So I don't have to do multiple tests. One graphical summary solves the purpose. Look at your p-value and then take a decision, normal or non-normal. Normal, then look at mean. Non-normal, then look at median. In the other one, you don't get this information. You don't get like a lot of information. This is a complete package. When you look at graphical summary, it gives you every possible clarity about the analysis that you need to do. We will keep coming back to this again and again because there's a lot of analysis which is already done here. We'll be learning this in the entire measure phase because this is like a lot of stuff in here. So first of all, remember one thing, we know what is mean, what is median. We understand that. We know what is normal, what is non-normal. How do we check it? This is the name of the test. And we will perform this test. We'll get to know whether data is normal, non-normal, looking at p-value, and then we will take the decision. Should I be looking at mean or should I be looking at median? We know where to get that p-value. It's right here. That's it. And we keep coming back. So I'm just going to keep it like as it is. I'm not crossing it off. Now, two methods of finding central tendency. There's one more. So mean, median, we are done. There's one more method, which is mode. Mode is also a method for finding central tendency of the data, but not used in a numerical data set. What is mode? It's a frequency, highest frequency in the data set. Now, let's quickly understand what does it mean and when do we use mode? Why? Because if it's a numerical data set, a number-based data set, either data will be normal or data will be non-normal. So I will either use mean or I'll use median. Then what is the purpose of mode? Mode is just the meaning. We just looking at mode and as to get the meaning. Where does it get used? I'll just quickly talk about it, but let's look at a data set. 1, 2, 3, 4, 5. Highest frequency. That means if there is any repetition, highest repeating value is what we're looking at. Is there any repetition? No. 1, 2, 3, 4, 5. No mode in this data. Simple as that. Mode is repetition. Let's look at this. 1, 2, 3, 4, 5, and 2. Well, 2 is the mode of the data. Why? Because it's repeating 2 times. 2 is repeating 2 times. So 2 is the mode of the data. 2 is the mode of the data. Well, what if I have this data set 1, 2, 3, 4, 5, 2, and say 5? So ideally, in this case, I have 2 modes. 2 and 5 are mode. Now, technically, what I'm trying to say here is you may not have any mode if there is no duplication, there's no repetition. You may have a single mode if there's one single value, which is highest repeating value, or you can have multiple modes if there's a tie. So that mode is just the highest repeating value. Numerical data sets, sorry, doesn't get used. Where do we use? For discrete data sets. For discrete, technically non-numerical data set like binary, ordinal, nominal, that's where you use this. Wherever you are talking about binary, ordinal, nominal, like yes, no, pass, fail, that's when, how do you get the center? Because you can't find average of yes and no. You can't find an average of excellent, good, average, bad. You can't find a median for them. So because they are text, for text, how will you find the averages? How will you find median? To find the center of that data, use mode. Mode, the basic logic, always remember, majority wins. That becomes the mode. Now, say there is a group of 10 people in a room, and we just took their opinion that which shoe brand do you prefer? So one person said Puma, another person said Puma, somebody said Reebok, somebody said Nike, another person said Nike, and then say you got like 5 people done. Then we got Nike, and we got like Reebok, we got Nike, and we got like a Puma, and we got Nike again. Simple as that. Highest repeating value, Nike, 1, 2, 3, 4, 5. 5 people voted Nike. Perfect. Nike becomes the mode of the data set. So in this kind of data set, which is text based, you use mode. It's like when there is an election which happens, there are different parties which contest and they want to win the election. The party which gets the maximum vote wins it. Mode. Mode is majority wins. Simple as that. It's only going to be used when you have a binary, ordinal, or nominal data, which is more of a text based, where you cannot do the mathematics there. So you use mode as a method of finding central values. So 3 methods of finding the center. Data analysis. Are we all okay with it before we move ahead to next topic? Is it okay?
All good. Thank you.
All right, perfect.
Yeah, good.
Perfect. Let's have a look at two more students, I guess. Yeah. Now we've done some bit of analysis ourselves already. Uh, the mean of this two students like is same, 75, 75 average scores. Median is fortunately same, 76, 76, and mode is also the same. Well, we know there's 3 ways we can find the central tendency to do analysis, but in this case, the mean, median, mode, they're all same. Well, does it mean there is no difference? No, absolutely not. There is a difference in the data set, and student A and student B are definitely different from each other. How would we explain the difference? Because we exhausted everything. In central tendency, we knew 3 things. There we are done. No differences as per central tendency. So just by looking at center, you cannot always get your answers. It is 50% analysis. Whenever you're looking at central tendencies, you're looking at averages or median only, you're only getting 50% of the picture. Half analysis, that's it. So if you have been taking data, if you've been taking decisions just by looking at averages, sorry, you have been doing a blunder there, because you've been only looking at doing 50% analysis. Remaining 50% analysis will complete your complete analysis. So that's where the next part comes into picture. The first was central
Dispersion.
tendency. Yes, absolutely. Dispersion of the data, spread of the data, distribution of the data, variation in the data, whatever you may call this, that's the area we are going to cover. Technically, this is the zone we are for the first time getting into Six Sigma. Six Sigma, what does it do? Reduce variation. This is the study of Six Sigma, because Six Sigma deals with variation. That doesn't deal with your center. Six Sigma is all about variation. That's the area we're going to talk about. So Six Sigma works here. That's the area where Six Sigma works. Variation. That's where we would be focusing on. Entire analysis, entire study around the Six Sigma journey will be all talking about variation. So now, what are the metrics of variation? We have range, we have variance, we have standard deviation. So I would rather take the range in the end, because they will be attached to something else, and take up this thing first, variance and standard deviation. So 3 metrics there, 3 metrics here. That's what we are going to be looking at. Now, variance and standard deviation will just to take it next to each other, because technically they are more like same. Let's understand this. Now, we are talking about variation and we are talking about variance. Variance is a metric. It's a metric through which we study variation. So variance is a different stuff. To study variation, we can use variance. That's a metric, like mean, median. mode. Similarly, we have variance. When we use variance, we study variation. When we use standard deviation, we study variation. So variance is a metric. Let me write down the basic definition of it. We'll learn the definition, and based on the definition, we'll solve this variance. What do we mean by this spread, variation, variance, standard deviation? What does it mean technically? Let's understand it. First of all, the definition is squared average distance of each data point from mean. Squared average distance of each, well, sounds like a fancy statement, but we'll come back to that. It's average distance of each data point from mean. That's the definition of variance and standard deviation, simplest form. But sort of let's understand what does it mean further. We going back to my favorite data set 2, 5, 7, 9, and 12. Small data set. I want to find what is the distribution, what is the spread, what is the variation in this data. Well, I want to find it out for this data set. What is the variation here? But what is the way, how, when you want to find out variation, all it's talking about squared average distance of each data point from mean. From mean, how much is the distance, how variation, how much is the spread from the mean, average distance of each data point from the mean. So from the mean, how much data is moving out. In central tendency, what we were trying to learn is how much data is close to the center. Where is the center? In variation, we are trying to find how much it's away from the center. So first of all, let's find the center. That's when we'll be able to understand how much it is moving out of the center. Let's find it out. That's what is distribution, spread. Let's see. Average. My average is 7. We already know that, by the way. So 7 is my average. Before we solve this, I would like to graphically show you so that we get the objective clearest when I hear the word variance, when I hear the word standard deviation. At least the image should be clear in front of me as to what am I talking about, not the numbers. What am I talking about? Let's try to have a sort of a basic image in front of us. What does variance and standard deviation means? This is my mean, what we say 7. A line which says this is the mean of the data, 7. First value is 2. So 2 will be less than 7, so 2 will be somewhere here. This is 2. This is distance of 2 from the 7. Variation of 2 from the 7. This is distance number 1, or variation or spread. How much data is away from the mean. This is variation number 1. Okay. Then we have 5. 5 will be a little closer to the mean here. Say 5 is here. This is the distance of 5 from the mean. Variation number 2. Okay, then we have 7. 7 is right there on the mean. So whatever is 0 variation, but it's right here. Third value. Then 9. 9 will be more than the 7. So 9 is somewhere here. This is variation number whatever 4. And then we have 12, which is little away from this. So this is 12 and this is variation number 5. Bottom line, job done. That's what I wanted to find out. What is that one I want to find out? Variation. What we want to find out is average variation. Simple. In average, we have been calculating averages. So how did we calculate average? We have calculated average as sum of all the values divided by the count. That's how we did average. Here we want to find average variation. So what we will do, sum all the distance, sum all the variation, and divide by the count. There we did sum of all the values. Here we'll do sum of variation. So distance number 1, distance number 2, distance number 3, distance number 4, distance number 5. Add them and divide by the count. Your average variation will come. Simple as that. That's what we are trying to find out. Average variation. Is this okay with everyone?
Yes.
Yeah. So like average variation, when you talk about like here 2 and 7. So this is 5 and here 2. So that 5 plus 2 is 7, here 0, and again here's
No.
2.
2, how much 2 is away from the 7, from the mean?
That's 5, right?
Yeah, so this, no, yeah, minus 5, minus 5. This is minus 5.
Oh,
Because
yeah,
2 is less. Yeah.
absolutely. Minus 5.
This is one other. So now we'll solve it with numbers, but image wise, I wanted to make sure that at least we understand there are different distances. Every value is some distance away from the mean. We will find the distances and we'll take the average. Simple as that. That's what we want to do. Okay. Let's clear up these drawings and let's go back to the calculation part. Let's get the basic stuff. When the image is clear, the calculation becomes easier. This is my mean of the data. So I'll write down the mean, which is 7. And let's get 7 here. Now we'll find distance from mean. So that's the same distance from mean. That is what we wanted to find. Distance from mean is right here. So distance from mean will be 2 minus mean. This is minus 5. This is less. Okay, I understand this less than 5, less than 7. So I will copy paste the formula. This is minus 2. 5 minus 7 is minus 2. 7 minus 7 is 0. 9 minus 7 is 2. 12 minus 7 is 5. So we got distance from mean. Every data point, distance from mean. Like now we got the distance. Let's do the sum and divide by the count. So we do the sum of all the distances. Well, that's a problem. That's a problem. We're getting a 0. Now, what is that we wanted to find out? Average variation. Simple layman language. We not want to make it technical. Objective is to understand the essence. So average variation is what we wanted to find out. We wanted to find sum of variations or sum of distance, and we wanted to divide it by count. But unfortunately, because sum of distance is coming as 0, 0 divided by count will give me 0. Is the average variation 0? No. That is a big problem. Why we're getting 0? Because this plus and minus, they're canceling each other. Why? Because it's mean. Mean is the center of the data. Half data will be less than the mean. Half data will be more than the mean. The positive, negative will always cancel each other. So we are getting a 0. So we have to take help from arithmetics, and that's where the arithmetic part will come into picture. And what we will do is we double up everything. We square up everything. So minus minus becomes plus. So what we do, we square the distance. So you double up the distance. So let's do the square and let's understand how it works here. Square up the distance. So minus 5 multiplied by minus 5. So everything will get doubled. So minus minus becomes plus. So I will do square of distance. So minus 5 multiplied by minus 5. That becomes me positive 25. So minus minus becomes plus. I copy paste this formula. So minus 2 multiplied by minus 2 becomes positive 4. 0 multiplied by 0, 0. 2 into 2, 4. 5 into 5, 25. We've got the distance here, but unfortunately now we are not getting sum of distance. This is sum of doubled distance, not the actual distance, sum of doubled distance. So you can't get the direct average. You won't get the average variation. You'll get doubled average variation. That's what you will get, because you're not getting a simple distance. You get a double distance. So you'll get a doubled variation. So in a layman language, just trying to put some words here. So unfortunately, you will get squared, not normal variation, squared average variation. That's what you will end up finding out, because you don't get a simple distance, which will be sum of squared distance, double distance, and divided by count. So unfortunately, you don't get a single distance, simple distance. So we already have this sum of square distance, which is 58. So let's get this sum of squared distance, this which we have as 58. We already have got doubled distance, sum of it, well, job done, divided by the count. Now, here is what we have to keep one aspect in mind from statistics. Like if you pick up any statistical book, there will be two terms that you will come across, which we will be talking later also: sample and population. Population, the count of population is always in every statistics book. This is how it is. Sample count of population is always taken as n. Population means everything. Say I want to know average height of people or average income of people living in Dubai. That's a simple, like, see, that's my population. Everyone in Dubai living, everyone living in Dubai, I want to find their average income. So first of all, everyone in Dubai is n, population. And sample, by as per statistics, is fixed as n minus 1. Whatever the count you have, minus 1 is the count of sample. That's how it's taken. N minus 1. It is standard thumb rule for every, like any pickup, any statistical book. This is how you will find it. And what is the logic behind it? Let's understand it. I wanted to know everyone's income. Everyone means everyone, practically everyone. Even if I miss out one single person, it is no longer population. Population means absolutely everything. Even if there's one person less, or if even if there's one person who has not given you the data, you are no longer working on population, you are working on sample. That's what we are dealing with. So we can never ever have a population data. Why? Because it's not humanly possible for you to get access to the entire population. So in statistics, we always deal with samples. So if there's, like, say, 10 million people, for example, in Dubai, even if there's 1% less, you are dealing with a sample. That's the logic of this n minus 1. So anything, even a single value less than the population, is the definition of a sample. So here, what is my sample count? 1, 2, 3, 4, 5. The count instead of 5 will be, and that's how, as per the statistics, the count value will be used as n minus 1, which is what we will be using. 5 is the total count, minus 1 will be used, it will be used as 4. Instead of 5, we will be using count of 4, n minus 1, every time. Whenever we talk about sample, we always talk about n minus 1. That's the definition of a sample count, n minus 1. We always deal with a sample in times in the language of statistics is all about sample. We deal with samples. N minus 1 will give me a count of sample as 4, which will come here. That, if I do the maths, which is 58 divided by 4, it will give me 14.5, which is what it is, squared average variation, which we actually call as variance. This is nothing other than variance of the data. That's what it said. Variance is squared average distance of each data point. And squared, a doubled average distance. Assume there is an average variation and you're looking at the average variation using a magnifying glass. It's doubled. Did you ever wanted to find out this doubled variation? No, sorry. I never wanted it. But I never had a choice. I was getting a 0 and had to double up everything. So unfortunately, never wanted to calculate this, but I had to. Otherwise, there was no solution. So this gets calculated, yes. But I still want my average variation, the actual variation, not the doubled one. So what do I do? To cancel the doubled impact, or the squared impact, the double thing impact, what we do is we square root the variance. Whatever variance we've got, we square root it. This is the symbol. If you all can remember this is the square root part. So we square root the variance, which we will be able to give us the actual average. The doubled part gets cancelled because of the square root. When you do square root, pretty much that double thing goes away. So once we get our variance, we can find the average variation, not the doubled one. So which is what we call as, say, we call it as average variation, or you call it as standard deviation, or how do we calculate this? SQRT, square root of what? Variance, the doubled average. If you square root this one, this is what you get as average variation in the data, which is what we call a standard deviation. Standard deviation is calculated after you have got your variance. Variance is calculated, and from variance you end up getting the average variations. First you get the doubled one, and then you square root to get your average variation. Now that's how the calculation happens in the back end. You want to solve anything manually, you can do this basic math by hand also. You can calculate this. You can use Excel, you can use Minitab, you can use a lot of methods. Bottom line, everything follows the same process. So if you understand the basic law, just let me know if in case we are okay with this. Is it okay with everyone?
Clear.
Yeah, it's clear.
Okay. We have a direct formula also, which we can use. So this was just to make sure that at least it's clear to us when we're calculating this standard deviation and variance. So standard variance is VAR, open up the bracket. This is the data, close the bracket. Well, Excel is doing exactly the same maths in the back end to get you to this 14.5. Standard deviation, STDEV, open up the bracket. Excel is doing exactly the same maths in the back end to get you this value. Same stuff, exactly the same thing. So technically we could have just used a variance and standard deviation formula, but this may not help me understand what does it mean, how is it coming. Bottom line, that was the purpose of doing this basic maths. Do we really need to do this? And the answer is no. Have a look at your Normality test, did you do that? You got your standard deviation already calculated. If you have a data, you checked your normality, you already know all this stuff. Standard deviation, variance, it's already calculated. You don't have to do this multiple calculations, just one graphical summary. Your job is done. You know how many data points are there, how many data points you're checking, what is the mean, what is the standard deviation, what is the variance, everything gets calculated. So that's what the median also. So pretty much it's a single snapshot which gives you every possible information which you need to study about the data. Moving on, these are the two metrics. We have one more metric which is range. This variance, standard deviation, then we have range. Now, range could become a lengthy topic, yes, and we will be trying to understand that, but let's quickly okay, is it okay? Shall we take the 10 minutes break now, because I don't want to break in between?
Yeah,
Yes, please.
Okay, let's take a 10 minutes break and be back in 10 minutes as per your respective time zone, and we'll resume with the range, because this is going to be an interesting part which we'll be learning next.
Okay. Thank you.
Thank you. Thanks.
Hello?
Uh, so are we back from the break?
Yes.
Right. All right, perfect. So before going on the break, we covered up the variance and standard deviation. The last part in the variance part is variation is about study of range. Now, range in general looks very, very simple because range is just the maximum value in the data minus the minimum value. That's the range of a data set. So any range of the data, like we all had this explanation, like the maximum value is say 78, the minimum value is 72. So 78 minus 72 is 6. So this data has a range of 6 or variation of 6. In the language of range, we have range of 6 here. As compared to this one, which is 84, which is maximum. Minimum is 67. So 84 minus 67 is about 17 data points, I guess. So yes, so range is very high here, which is 17 as compared to 6. This is more consistent data. This has got high variation and the range is 17 here as compared to 6. So range can be easily explained and understood, but with the range, there's something else which has been added now, which makes it even more interesting, which is what when we study range in terms of a graphical plot. Now, uh, have we worked up on a box plot before? Just want to check. Did we work on box plot?
Yes.
Yes, in the green belt.
Okay, perfect. So box plot, which is also known as box and whiskers plot, either you call it box plot or box and whiskers plot, meaning is same. So otherwise, range basic definition is very simple. Highest minus the lowest value will give you the spread of the data. When you study this on a box plot, that's when it becomes very interesting. But before we discuss anything about this, remember one thing very clearly. This is a median based plot. So for box plot, you can do work on, you can use a normal data also. You can make a box plot out of a normal data, and definitely for non-normal data, because non-normal data can only be tested on a median. Normal data can be tested on anything, mean or median doesn't matter. So this single tool can help me with both the data, normal or non-normal doesn't matter. It's a median based plot. So what I'll do is I'll quickly use one of the data set which we have in the file. Like we have this file, I'll use this and sort of try to make a box plot, explain the box plot, and then we'll use the entire data set to make some inferences out of it. First of all, I do need to explain the box plot. When we make a box plot, what do we read in a box plot? Let's kind of check this out. So copy paste this entire data. This is already there in the Google, the drive, the data you must have downloaded. Now, first thing we are going to check for a simple box plot. First, let's understand what to read in a box plot, how to interpret a box plot. And when we understand it, that's when we'll go with full throttle, the entire data set for analysis. I will be making a simple box plot first. So I go to graph, go to box plot here. It's a graphical plot and the favorite management tool nowadays, box plot. To start with, just a simple one, because we want to study a single box plot and read and understand it. Then we will do the other one. So click OK. What is it is asking is like, what data do you want to analyze? Well, I want to analyze this IT ticket closure time. So there's some IT ticket closure time data, basically, and we want to analyze this data. The management has given us a problem that they believe that we are taking too high time to close an IT ticket. There's so much of backlog created. We are not closing the tickets in time. So there's a project which needs to be done. So the management has set a target that if your ticket closure time increases more than 20 minutes, I'll call that as a defect. So till the time you are able to finish your tickets closure time within 20 minutes, it's a good thing. So it's a quality. Anything more than 20, it's a defect. How do I put my target here? I go to scale, Go to reference line, and at the reference Y value, I put my target, say 20 minutes, whatever the management gives you, the project target, we put it here, 20. I click OK and I click OK. That's how a box plot looks like. Simple, but very important. A lot of information in it just by looks of it. If I take my cursor here, it's going to give you some information. That's what we need to read and understand first. I'll go back to my Excel, sort of type in all these values so that we can make some sense. Q1, then it 15.7237, 15.7237. We have got median 18.7627, median 18.7627, and then we have Q3 21.5030. Q3 is 21.5030, and then we have IQ range. Forget about it. We can get this viscous. Let IQ range. I'll just type in IQ range. I can get that. Viscous 2. That's what I want. Viscous 2 is okay. 9.42704. 9.42704 and 26.0608. N is equal to 181. And I know this one already. Why? Because it's Q3 minus Q1. That's what is 5.773. 5.77934. 5.77934 or whatever. 934. 5.77934. Okay, perfect. So we got these values. Let's understand and interpret these values, and then we shall move ahead with the box plot, the Minitab version there. So we just try to read all these values and understand what does it mean. So first of all, we know it's a median based tool. Box plot always did it like the data must be sorted. Median means data is sorted. In a box plot, the maximum value is always on the top. The minimum value in the data is at the bottom. The data is sorted, yes. So whatever may be the data in a box plot, the maximum and minimum order will be like this, a top to bottom descending order. That's how data is plotted. This is where the median is. Median is the half of the data. Median divides the data into two equal half. Half data is more than the median. Half data is less than the median. Simple as that. So this is 0% data. This is 100th% data. This is my 50th% data where my data is being segregated into equal half. Now, just help me understand if I were to find a median in this lower 50% from 0 to 50%, what percentage would be the median here?
25%.
Perfect. Perfect. That is what we call as Q1 or quartile 1. Quartile 1. If I want to find out the median here between 50 and 100, what percentage would that be?
75.
Thank you. Perfect. That's what we call as quartile 3. Quartile 3. And median can be called as quartile 2, which is fine. So bottom line, what median, this quartiles mean quarter is 25. So median divides the data into two equal half, 50% each. Quartiles divide the data into 25, 25, 25, 25 quarters. First 25% data, the lowest 25% data, because data is sorted. The next 25% data, the next big 25% data, and the top 25% data. So data is segregated into 4 equal half. Keep this in mind. Every section has equal amount of data. This 25% data, the number of data, it's equal as you have number of data are equal here, the number of data is equal here, the number of data is equal here. Every section has equal number of data. Now, technically, if I go back and look at the image, this box, This is the median. This is the median. This is the minimum value. This is the, let me just get these values here and then we can come back. This is the minimum value. This is the maximum value. This is the median. So data, so half of the data is more than the median here. This is half of the data. Half of the data is less than the median. So whatever total number of data is there, half data is more than this, half data is less than this. Further, this top 50% was bifurcated into 25, 25. So 25% data is here. 25% data is in the tail. The tail has 25% data. This box has 25% data. This box has 25% data. And this tail has 25% data. Every box and every tail has 25% data. The only thing you got to look at is the size of the box and size of the tail. This tail is pretty long. The data is scattered. The range is very, very high. This data is pretty long. This box is small. Although both tail and date box, they contain equal number of data. This data is very, very compact, less variation, small, but variation, the number of data is same. This tail is pretty long. The data is scattered. Same number of data, but scattered. This box has same number of data. Again, this is also compact. This tail is little bigger here. This data, the tail seems to be bigger here. The boxes are very, very compact. So whenever we are looking at a box plot, all we got to be looking at is the size of the box and size of the tail. Why? Because every box, every tail contains equal number of data. So here, if I want to sort of draw this, this is how it is. This is my box plot. This is the median. This is the tails. That's how it looks like. This is the data we are looking at. So minimum value, 25%, median, 75% and 100% value. That's what we have in the box plot. Now, are we okay with this? Are we able to make sense out of this for now? There's some more bit which is left out, but yeah. Is it okay?
Yes.
All right. Let's clear this drawings. Let's do some calculations here now. We all know range. Range is maximum minus minimum. So let's find the range in the lower tail, the tail, variation in the tail. Let's see variation in the tail. Let's put the values. Rather, I forgot to put the values. We got Q1, quartile 1. Let's put the value here, quartile 1. Median, we know median is this. Quartile 3, we know this quartile 3. IQ range, I will come to that. Whiskers are the whiskers, boxes and whiskers. Box are the box, whiskers are also the tails. So whiskers, it says lowest value is 9.42704. 9.42704. That's what it tells you is the minimum value in the data, and the maximum value in the data is 26.0608. That's the maximum value in your data set. So pretty much we got a n is equal to total 181 data points. We are done with everything barring this IQ range. IQ range is called interquartile range, which is basically Q3 value minus Q1 value. So whatever you get is your Q3 minus Q1 will give you interquartile range. That's what you get as interquartile range. Simple as that. Now, technically, we have to find the range, variation in the tail, maximum minus minimum in the tail, lower 25%. Maximum minus minimum, that variation in the tail is 6.29. Let's find the lower box, maximum minus minimum. Maximum minus minimum is what range is. The variation in the lower box is 3.039. Variation in the top box is 21.503 minus this. Well, the top box has even lesser variation. So data in the center is very compact. This is like at the center median. So 25% here in the box and 20, which is very less variation, and 24% here, which has got less variation. So box in the center, 50% data in the center. Top box and the box below, they have less variation. Data is compact at the center. Let's see maximum minus minimum in the top tail. variation is high. So I know the variation is high in the tails, and the box, the variation is less. The center of the data is very, very compact. The tails are pretty big. That's what we see, variation is high. If you look at the image, that's what tells you the tail has a high variation. Boxes are compact. The tail is a little higher. So I get to see just by prima facie looks of it, it tells me that where is the maximum variation coming from. Now, other than this, there's some more elements that we have to look for. We will talk about, can I get these values on Excel? Yes, we have formulas. We can calculate these values on Excel also. These Q1, Q2, all that stuff, we can get it instantly. But before we do that, just a quick question to every one of you. Looking at this, we still kind of working on these two stars. We'll talk about these stars later. This is my target line, which is 20 minutes. Remember the time, the target is to reduce the ticket closure time, which is very high. Management wants you to reduce the time. 20 minutes, the moment you cross 20 minutes, it's a defect. Anything less than 20 is good. So what is my fail percentage in this data?
12.5 plus 25%.
Absolutely correct. Anyone else wants to predict why is that? How much, what is the fail percentage here?
62?
No, fail percentage.
Fail percentage, I
And
think more or less
Yeah.
32 something. 30% plus.
57?
Yeah,
yes,
37.
yes. I would agree with that.
7.5 around.
Absolutely, yes, absolutely. Thanks for sharing that. Yes, that's correct. Anything more than 20 is fail. Yes, we understand that. Anything more than 20 is a defect. Perfect. Does this tail contain 25% data? Yes. Is it above 20? Yes. So 25% fail, done. This is failed. This box has 25% data, and this is sort of bisecting it midway. Sort of midway. So I would say 12.5 is here and 12.5 here. So sort of midway, because this box has 25% data. So 12.5 is fail and 12.5 is pass. So this 25 and this 12.5, which will add up to 37.5. So just by looks of it, I know how much is my pass percentage or fail percentage. So this is about 12.5 above the line, which is fail, and this box says this tail has 25%. So this is my fail percentage just by looks of it. Is that okay with everyone?
Yes.
Yes.
Oh, all right, perfect. Now let's quickly look at a couple of more things, and then we go back to the all the box plots together. Right. So, but yes, let's understand about these asterisks and understand how can we get these values on an Excel. First of all, can I get these values on Excel? Yes. So the formulas are pretty simple. Say I'm randomly creating some random data set just to kind of give you all those values here. Ran between 10 to say 67, some random values. Can I get these calculated in Excel? Yes. So first of all, what I need is a minimum value. I need the maximum value. I need quartile 1. I need quartile 2 or median. Let's type in median also. Quartile 3. Quartile 3. I need IQR. That's what we need. And then practically that's what we have in these values. So let's calculate them. Min for minimum. Can I find the minimum value? Yes. Can I find the maximum value? Yes, I can. Max for maximum. Quartile, type in quartile. Quartile, open up the bracket. Take the data, comma, 1 for quartile 1. Let's find quartile 2. Quartile, open up the bracket. Take the data, comma, 2 for quartile 2, which will be same as median. Quartile 2 and median are same. Type in median, open up the bracket, take the data, quartile, this is the median, same as quartile 2. Quartile 3, open up the bracket, take the data, comma, 3 for quartile 3. IQR is Q3 minus Q1. That is interquartile range. So formulas are very simple. We get it on Excel also. By the way, when we did the test, when we did the test before, the graphical summary. I can just want to redo that activity. See, everything comes here. Then did a graphical summary. This is what we got. Say, do I get the minimum value? Yes. Do I get the first quartile? Yes. Do I get the median? Do I get the third quartile? Do I get the maximum? I get everything. What I want, like everything is available. One click and I'm aware of every possible analysis. That's the same box plot. These are the two stars we've been talking about. But everything gets done. Single click. You don't have to do too many things. One graphical summary is a self-explanatory document. Tells you every possible thing that you need. But yeah, we still need to figure out what are these stars. These stars, we'll go back to the Excel. Now, if I take my cursor here on the previous, not this one, like so we understand what's in there. Now, let's take my cursor here. It says outlier symbol, row number 153, you have time of 33 minutes. It's saying it's an outlier value, exceptionally high value of 33. In your sheet, you go and check row number 153, you'll find 33 value, which is very, very high. It's been thrown out of the data as an exceptionally high value. Please treat this data separately. Okay, great. Row number 167, an outlier value of 6. It's too low and it's been thrown out of the data as an outlier value. Please treat this data separately. Bottom line, if you have data which has outlier features, it will be thrown out. And that's why box plot is so good, that you do not let wrong data mess up with your proper analysis. There's something which needs to be studied separately, be thrown out on its own, and you will be able to study the clean data. See, one-time exception cannot be made a rule. It cannot be a thumb rule for entire process. No, say you have 50 people working for you. Say it's a sales process. One person does 10 times of his target, and rest people are just managing 100%, 110%. No, that 1% cannot be made a guideline for everyone. So that's what the one odd exception has to be treated as the exception. So yes, boxplot does this job for you by throwing those values out. But how does it identify something as an outlier? What's the criteria? Well, it's very simple. Let's go ahead and check this out. So the upper outlier criteria, it is Q3 plus 1.5 multiplied by IQR. Whatever value more than this value will be thrown out. Lower outlier, Q1 minus 1.5 times of IQR. Any value less than this will be thrown out of that data. Let's do this maths. Q3, we already know Q3 value. Q3 was this plus 1.5 multiplied by IQR. IQR was this. Yeah, any value more than 30.17 would be thrown out. Yes, we had value of 33. That's what it says, 33. Yes, 33 minutes. And any value more than 30.172 would have been thrown out. And yes, that was the reason 33 was thrown out of the data. Any value more than this will be treated as an outlier on the upper side. Let's find for the lower side. Q1 is here minus 1.5 multiplied by IQR. Well, any value less than 7.05 will be treated as a lower side outlier, exceptionally low value. Yeah, we had 6 minutes here. Yes. So if you have outliers, don't worry. Boxplot will take care of it, and you would know when, where. Just go and scroll down, understand, do a root cause analysis. What happened in row number 153 or whatever this value was. Say row 153. Yeah, you see 33 minutes. Go and do a root cause analysis. What happened on this day? What was it? Because this is one odd case. You just got to treat this separately. So whenever you see those exceptional outlier values, that needs a special treatment. You can't make this a rule or a standard for everyone. Like 6 minutes, exceptionally low. Well, that needs to be studied separately. So that's why box plots are important in analyzing your data, and that's good in terms of cleaning up the data also. Yeah.
Sir,
Yes.
question. Yeah, quick question. It is very interesting. The outliers. How would we know if the outlier is affecting our mean or our median?
See, median it will never affect. Mean is only what gets affected, because median is only going to look at the center. So if there's a
Yeah,
really high or really low, it will be thrown out on the extreme ends because it will be sorted.
correct.
Mean gets influenced. Simply, if it's a non-normal data, it will be thrown. It will always influence the mean of the data.
Mm, okay. So if there's a outlier, automatically there's a
Mhm.
significant impact to the mean. Uh,
Absolutely, yes.
does it mean that we need to remove the outliers?
Technically, see, now at a green belt level, there are limitations. At black belt level, we would not have limitations. So we'll have multiple options. Yes, you can remove them,
Mhm.
or you can use them as it is also, because the black belts will be exposed to non-parametric tests. So at a green belt level, we generally end up dealing with the normal data. The black belt level, we will be having the luxury of uh, following the basic protocol of using the data as normal. So I can remove the data. I can use transformation methods. I
Yeah.
can use the non-parametric methods. So there are ways we can deal with it. And it's all your discretion. What is it that you want to do? Removing an outlier is also a viable option where you can treat the data and you can do a root cause analysis why that happened, but it's absolutely okay to remove the data
All
if
right.
it gets normal.
All right. Thank you, sir.
All right, thank you. Now,
Sir,
moving,
I have
yes,
one question. I'm
yes,
sorry to
please,
interrupt.
please. No, no, please.
Since we're talking about box plot and it works on median, so
Yes.
does it mean we can only do a box plot on non-normal data, or it doesn't matter to do it on a normal data?
You can do it on anything, normal or non-normal. See, non-normal data doesn't have a choice, but normal data you can use median also. In a perfect normal distribution, normal your mean and median are same. So in a normal data you can still use median. There's no problem. But in a non-normal data you don't have a choice. The only choice is median. So normal data everything is okay. You can do anything.
Oh, okay, thank you.
Okay, perfect. Now, just now, because we have done the basic interpretation, let's start using the entire data set to make some inferences out of this. We go to graph, we go to box plot, and in the box plot now we will be looking at groups. We will like to start comparing the data. Click on this, we select the data, which is ticket closure time. Now I would like to analyze this ticket closure time by what? Say I have ticket handlers. These are the people who are managing the IT ticket. Okay, well, let's compare them and see who is good and who is bad. So ticket closure time by ticket handler. Well, we have the same target, which is scale, reference line, and we have the target of 20 minutes. Now we would like to see how good or bad are these ticket handlers. Let's see. Now, help me understand who is the worst ticket handler we have got here. Worst ticket handler.
Nathan.
Nathan.
Nathan, yes. Anyone?
Nathan, yeah.
Okay, and the best ticket handler?
Vandana.
Vandana.
Absolutely, yes. Without any doubt. Vandana is the best ticket handler we have got here. What's the tentative pass percentage of Vandana? Pass percentage?
100.
No, not 100.
75%.
More than that. More than that. Why? Because you have got the tail, which is less than 20, which is 25% data. This box is 25%. This box is 25%. So 75%, any which ways you know it's below 20. This tail has 25% data, and I would say roughly 10% is here, roughly 15% is here. So I'll say 85% is my, like 80% or 85% is my pass percentage. Some anything which is crossing 20 is my fail percentage. So I'll say like 85% roughly. I'll say 10% is here, 15% is here, because every tail, every box has 25% data. The line is bisecting it somewhere, like I would say 10% here, and the remaining is here. More like approximate. And I guess we all good with this. Nitin. Nitin is the worst ticket handler we have got on the board. Let's then do one thing. Let's cross this off and get a quick comparison on the gender, which we don't want to be gender biased here, but who is doing a better job here?
Female.
Females are doing a
female.
better job, yes.
Female, yep.
What's the pass percentage of females?
Around
75.
Yeah, little above more than 20 because some portion is there.
yeah.
Yes,
Like
this is roughly
77,
probably
78.
add 1-2% more. That's it. Yeah, but yeah, more like that. Perfect. Now let's quickly moving on to next bit. Let's qualification of people. Who is my pain area here?
Postgraduate.
Postgraduate.
Graduate.
Postgraduates. We all okay with that? Postgraduates are doing horrible here because they almost like 50% fail. That's what we see.
Yeah.
It looks like.
More than 50.
Yeah, absolutely.
More than
yes.
50%.
More than 50%. Yes. Great. Let's have a quick look at the same thing. I'm not taking away postgraduates anywhere. Keeping postgraduates as it is, I would like to use shift. Now, do you still see postgraduates that bad? Or there's something else?
Night shifters.
Night shift postgraduates are horrible.
Yeah, they are
Morning
worse.
ones are great. Morning ones are like probably I would say
Yeah.
very good. Night shift is horrible. Let's see if we can further bring about some more flavor to this. Let it be as it is. Let's get the manager. Now it becomes clumsy, but let's still try to make some sense here. Where is the challenge here? Postgraduates, do you still see something else to it? I can take my cursor here if you want.
Puja, yeah.
Puja
is the problem.
Is Puja really the problem? So because so when I take my cursor, it says manager is Puja, shift night, handling postgraduates. So this is the one who's kind of messing up. Is Puja that bad? Sorry, absolutely no. I won't say because Puja here is doing a great job. So she's not a bad manager. Puja here is not doesn't have a night shift graduates. Puja again, if I come back here, Puja has been handling some night shift undergraduates, which is fine. But postgraduate seems to be probably that's not her cup of tea. If I look at this one single line, I'll tell you something else also. This Reena was handling a postgraduates, which is phenomenal. Can we do a work reallocation or team shuffling? Probably allocate the people assigned to Puja night shift and have Reena look after them because she is doing a phenomenal job. Although there is one candidate only, n is equal to 1. That's what it says. But it just helps you to uncover more aspects of the data when I'm looking at these box plots. I hope we all okay with this. I mean, it's making sense.
Yeah.
Yeah.
Right, perfect. Perfect. Okay, with that being said, what we will end the box plots here. So after this, we have like a couple of more things before we actually get going with the measure phase, because we need to get these basic some symbols and something understood before we start using the measure phase deliverables. So once this is being done, now let's we have next thing which we will be looking at into is population and sample. We already talked about this population and sample. So population is technically everything that about we are interested to know about, every single attribute. Now few symbols is what I'm trying to kind of portray here. I'm trying to make sure that we understand the symbol. This is what we're trying to understand. This is everything about the population, everything. Now as I was saying, like we would like to understand what is the average income of people living in Dubai. Everyone in Dubai is here. Now, can I get hold of everyone? Sorry, I cannot. So what do? Is I end up taking a sample out of it. I take a selection, a sample. I study all this sample, and based on my study of the sample, I do some bit of statistics, and that's what I get my sample average, I get my sample standard deviation. Once I've got this information, based on that, I'm still one. Was I ever interested in a sample? No, I was never interested in knowing the income of 10 people or 20 people or 100 people. No, I wanted to know it for everyone. Sample was never my choice. I had to do it, A, because I could not get the population data, and even if I can, it would have been too costly. So I took a sample, studied the sample, and then I'm making some inferences based on the sample about the population, because that is what I wanted to know. So that's how we move ahead when we kind of deal with the data. All this, whatever we have studied so far, it is all about sample statistics. Now, basic symbols is something which we got to keep in mind whenever we're dealing with, going forward we will be dealing with some data. When we see these symbols, first of all, the first symbol, if I talk about the average of a data in a sample data, average of sample data is denoted by x bar, x in a line on top of it. If you see this x bar, we are talking about average of a sample. But if you're talking about the average of the population, like the uh, income of everyone in Dubai, this is what we denote by the symbol mu. We pronounce this as mu. The pronunciation is mu, mu. We pronounce this symbol as mu. This is average of the population. This is average of the sample. So those 100 people, 200 people's income, that's average sample. And based on this, I predict what will be the average of the population, which is mu. Similarly, when we talk about standard deviation, we all know what is standard deviation. A small s is denoted as standard deviation of a sample. But if you see for the population, the symbol will be this. This is the symbol for population standard deviation. If you see the symbol, we are meaning population standard deviation. If you see a S, this is sample standard deviation. Similarly, if you see an S square, we're talking about variance, doubled average. That's what we talk about, doubled average variation. If you see S square, doubled one, that's your sample variance. If you see 2 here, again, that's for variance of the population. This is the variance of population. This is simple standard, this is standard deviation, this is variance of the population. Here it will be S, here it will be S square. So basically we should remember these symbols. Why? Because if we come across this, we should be able to figure out instantly, are we dealing with the sample data, are we talking about the population data? So all this while that whatever we were dealing with, we were there. So if we talk about statistics, it is going to be divided into your descriptive. Oh, my bad. Descriptive and inferential statistics. Descriptive statistics is all about historical data. It's already happened. So if when you work in an organization, there is generally a department who sends out daily reports based on what happened yesterday. The MIS department, that's what we say, MIS department, Management Information System. These people generate daily reports and they publish what is the trend and stuff like that. They look at data and they kind of analyze the data, historical data, all which has already happened yesterday, day before yesterday, last year, last month, whatever. Historical, it's all done. You have every single value available. You can do anything with the data. You can count, you can take the average, you can do standard deviation, you can do anything that we discussed, your mean, median, quartiles, everything. You make graph charts, everything is done. This is all what we're doing is analysis. You always analyze a sample data. You always analyze the sample data. But when you start based on your descriptive statistics, when you start talking about population. When you talk about future, you are talking about analytics. Analytics is about future. You haven't seen like population data. You don't have it, but you are interested in it. So this all we talk about prediction, forecasting. That's what it is all about. Inferential statistics, looking at sample, predicting about the population about which you have no idea right now. You collected a small sample, you did your bit of research analysis, mean, standard deviation, variance, and stuff like that. Whatever analysis that you've done so far, it's all descriptive. Based on this, we end up predicting about the future. Now that's what the journey is going to go there, because if you look at this stats, the two versions here, you see display descriptive statistics. Click on this, select the ticket closure time data, click on statistics. What all do you want to see? I want to see mean, standard deviation, variance. I want to see if need sum, minimum, maximum, uh, quartiles, all that stuff. Whatever you want, select this. This is all historical stuff. You can do anything about this data. Click on it. It will show you. That's all you have, your descriptive. All whatever you see, this is descriptive. You all know you can calculate this on an Excel also. Simple stuff. Practically, when you do the graphical summary, you get everything there. But the beauty of graphical summary is here it gives you descriptive statistics. This is descriptive. This is inferential statistics. Prediction, future, forecasting. This is not sample. This is future. This is future. We're talking about future. When you look at this, when you did this test right there, here it talks about something, confidence level, 95%. We will be talking about that because that's what is going to be playing a role in talking. So this is the descriptive part. This is the inferential statistics part. So anything that we did before, all descriptive. Now we're stepping into the inferential part of it, which will take us to the next journey that we have to kind of carry forward. So when we are talking about inferential statistics, when we want to make prediction about future unknown territory, three elements is what we will be concerned with. We should be clear about. One is confidence level. Confidence level. Confidence interval and margin of error. These are three things which should be, the concept should be clear. What do they mean? Simple as that. The rest, everything will be taken care of, because that's what is the basic need from analysis perspective. Now, we're taking a small, simple example just to kind of read and understand what do we mean by this. Say, I have been traveling between my home and my office for good, like I've been taking note of the time. The moment I start from my home, I reach my office, I take down the time. I note the time. How long did it take today? So for good 30 days, I did this activity, and I have got now travel time data for 30 days. And this travel time data for 30 days shows that on an average, I take 24 minutes. Average 24 minutes for office commuting time. That's what it tells me. Now, that's average for the 30 days. This is my descriptive statistics. It tells me how much time on an average I take to reach my office. Now, if somebody would ask me how long do you take to reach your office? Well, I'll say on an average about 24 minutes. Would you always reach your office in 24 minutes? No. So I'm expected to give how much time would you take to reach office? I'll say I'm just now cooking up some stories here. That's say I would roughly take about 22 minutes to say 26 minutes to reach my office. How sure are you that you will always reach between 22 minutes and 26 minutes? No, sorry, I'm it's not always. I'm sort of 50% sure that like 50% of the time I should reach office between 22 minutes and 26 minutes. Well, yeah, there are chances where what if I don't find any traffic? I could reach earlier also. If I get more traffic, then it might take more than 26 minutes. But on and like 50% of the time I should be there in office within 22 to 26 minutes. Okay, great. What if I give some bandwidth? I say like 20 minutes and 28 minutes. Like, how confident are you now that you will reach office within 20 minutes and 28 minutes? Well, I'm sure like this big range I can work with. I'm more confident this time. Well, I'm sort of 90% confident that I'll reach office between 20 and 28 minutes, which is pretty big time range. Yeah, 10% still can be here and there. Why? Because if I don't get in traffic, I will reach before 20 minutes. And what if I get a lot of traffic? Well, it might take more than 28 minutes also. But 90% of the time, yeah, I'll be there on time between 20 and 28 minutes. What if I give myself some more bandwidth, say 18 minutes and 30 minutes? Well, this time, well, I'm more confident about my office reporting time. So I'll say I'm sort of 95% sure that I will reach office between 18 minutes and 30 minutes, which is pretty big range. Yeah, but 5% chance is still there. Weird things can happen. You can't predict everything. Pretty much the last one, I would not keep going on and on with this. 16 minutes and say 32 minutes, which is pretty big range. Say 32 minutes. I'm sort of 99% confident that I'll reach office within this time frame. Yeah, 1% weird things can definitely happen. You can't predict everything. So you can go on and on. You can be 99.999999% correct. 100% sorry. You can never ever be 100% confident. Why? Because you're dealing with sample and any unforeseen weird things can happen. So 100% confidence is just a myth. You can never be 100% confident unless until you talk about population data. Population data means you have all the data. You can be confident. Yes, it's all. No. Here we're talking about that small sample data, like a 30 days data, 60 days data, still a sample data. Based on that, you're predicting something. Well, future hasn't happened. Things can happen differently. Yeah. So 100% confidence is not possible. So crux here is when you have some sample data, you've done your descriptive statistics, and you want to now predict the future, which has not happened. You always predict at some level of confidence. How confident are you about your prediction? Well, I'm 50%, I'm 90%. Well, who is going to believe you if you're saying I'm 50% confident? Well, nobody wants to believe you. Yeah. Industry wise, the most accepted confidence level are these 90%, 95%, 99%. Well, out of these, also there is some more differentiation here, but that's what is the one we would generally see. 90% confidence was a great confidence level. But yeah, still leaves 10% chance. 95%, yes, definitely better. And then obviously the great, like it's very, very good confidence level. People will trust you, and you would even be confident about your predictions. We're 99% confident that yes, it is going to happen. So that's what it means. Whenever you make a prediction at some level of confidence, you get a range, some range. Say 99% you got this range, 95% you got this range, 90% you got this range. This range is called confidence interval, the range. So it tells you the range. So when you make a prediction at some level of confidence, it gives you a confidence interval, which tells you how your population behavior would look like, how it will range. So pretty much that's what it tells me. And how does it get created here? It is created by the virtue of margin of error. Let me just get this here. Margin of error. So how margin of error it comes in play. So 24 plus 2 minutes and 24 minus 2 minutes makes it 26 and 22. So I'm working with a margin of error of plus and minus from the mean. Plus 2 minutes from the mean. What am I pressing here? plus and minus 2 minutes from the mean. Okay, that's what I was. Okay, plus and minus 2 minutes from the mean, which constructs 24 minutes, which is average. 24 plus 2 is 26. 24 minus 2 is 22. So a margin of error of plus minus 2 minutes would be making this range for me. Similarly, a margin of error of plus minus 4 minutes, 4 minutes plus the mean, 4 minutes minus the mean, which is making this range for me. Similarly, plus minus 6 minute was making the range here, and plus minus 8 minute was making the range here. So mean plus minus these many minutes is making your range of, and which is giving you confidence interval. Now, couple of things we got to keep in mind from here on. Let's talk about confidence level first. When we are saying confidence level, very rare companies, not industries, companies use this level. Very rare. Only in some manufacturing companies we've seen this, but very, very rare. This is standard thumb rule. Everyone uses this 95% confidence level. Everyone. Even if you talk about this mini tab, let's say this is what we saw here. Graphical summary, 95%. Set default. Default. Pick up any statistical book, you see 95%. Pick up any statistical software, any software in the world, you will see 95%. Can you change it to us? Absolutely, 99, 95, whatever you want to do, you can do it. Default is always 95%. Well, why we work with 95% when you can work with 99%? What's the fun in, well, does this means that we are 95% sure that my prediction will be correct. Why are you working with 95% when you can work with 99%? Yes, absolutely. But yes, it comes with a cost. There is a cost for everything. There's no free lunch. So yes, this confidence level will come with a cost. So higher the confidence level, the more will be the sample size, the bigger will be the cost of the project. So if you increase the confidence level, yes, the sample size will increase. Yeah, very rare industries, not companies, but industries at all, as a whole, use this. Now, what industries? Aviation, pharma, and all those space, like those critical industries, the life and death situation is at stake. Now, when you go for 99% confidence level, is my sample size going to be huge? Absolutely, yes. Do these guys have a choice? No. Well, let it be huge sample, let it be time consuming, let it be costly affair. Sorry, these guys don't have a choice. So yes, if it's expensive, let it be. Well, they don't have a choice. But for everyone else, yes, we can still work with 95% is a great confidence level, a good confidence level, and we get a manageable sample size. So it's not a big cost, which we want to. When we can work with 95%, pretty much gets me a good confidence level. So in general, everyone works with 95%, unless and until your industry needs a 99% confidence level, please go and use it. It's editable. Default will be 95%. So that's the confidence level we're talking about. Now, when you make this prediction, you get a range. That's what the range is all about. Now, how is range created? Based on the margin of error. Now, when your margin of error is small, your predictions are more compact, more compact. Let's take like a random example so that we can make more sense out of this. Like your boss would ask you, well, can you tell me what is your sales projection for this month? And my response is, I think we should be able to do like $10,000, or like between 10,000 and say $90,000. Well, my boss is going to laugh at me. Again, the sales prediction I'm giving you is like 10,000 to $90,000. Well, what kind of range is this? I'm sure you'll do something in between that. It's a very, very big range. Well, obviously people will not be happy to hear a very big range. It doesn't give confidence, like it doesn't look like a prediction. It's anyone's, but obvious. It will cover up anything. You will do something in between this range. What if I would have told, like, well, based on the trend I see, we'll do something between $55,000 to $65,000. That makes more sense. At least it looks like some prediction, some conviction is there. And like, so technically, when I will see a very big range, that means a big margin of error, I'm not that happy with that. I would rather want, if I'm working with say 95% at confidence level, I would sort of not like this big range. I would love to see a very, very compact prediction, which is where people would be happy to hear that prediction. Well, that's compact, very, very accurate. But yes, uh, as you want to reduce, as see, it works the other way around. If you increase the confidence level, the sample size increases. If you want to reduce the margin of error, you want to be more accurate, everything comes with a price. So the moment you reduce the margin of error, your sample size will increase exponentially. So see, bottom line, the cost is your sample. And when we do a sample size calculation, we will be getting to the calculation part. That's where all this will come into formula. In a formula, you will see that this is working as a denominator. So pretty much when we look at formula, it will get clear. But remember one thing, the thumb rule. If you plan to increase confidence level, sample size will increase. If you plan to reduce margin of error, sample size will increase. Bottom line, more accuracy comes with additional cost. To be more accurate, you got to give me more data. If you give me less data, I will give you vague answers. If you give me more data, I will have more information. I will be more confident about it. Yes, you want to be more confident about it. You want to be more accurate. Please give me more information. The more information you give me, the more accurate I will be about my predictions. So when I look at this data and I do a graphical summary here, what it tells me, I am 95% confident. What? Let's read this and we'll understand. For this sample data, which is fixed, this is not going to change. 181 sample from whatever process we have picked up, we picked up some sample data, which is 181 samples. It's a normal data because p-value is more than 0.05. The data is normal, so I can tell you that the ticket closure time on an average is 18.643 minutes. That's what we've been taking to close the tickets, the IT tickets. But obviously, when we pick up a new sample from the process, will this average change? Yes. If we increase the samples, will the average change? Yes. If I reduce the sample, will this average change? Yes. For this sample, yes, this is going to be fixed because this is all 181, which I have. I know this is the average. So that means the process, the huge process, the population from which I have picked up this small sample, that population will have different averages. It's just that this sample that I picked up, this sample has this average. When if I go and pick up different sample, this average will keep fluctuating every time I go to the population, pick up a different sample or increase this sample, reduce this sample, change the sample altogether. My averages will keep fluctuating every time. What it tells you that we are 95% confident that your process, your population average will range between 18.07 and 19.2. And how confident are we? We are 95% confident that your population average for this sample it's 18.643. But in the population from which you're picking up this sample, the average will range between 18.07 and 19.2. Yeah, there's 5% chance it can be less than this, it can be more than this. But 95% of the time, you will always find the population average between this range. Same goes for the median also. With 95% confidence, the median will range between this. Similarly, 95% confidence with the standard deviation will range between this. All predictions are at 95% confidence level. If I want to make the changes, yes, why not? We can do this at 99% also. Do this. Who's stopping you to do that? At 99%, the ranges have expanded. So when we look at the calculations, we'll understand this, the formulas and all there. But bottom line, you can make changes as per your will, as per your organizational requirements. You can make these changes. And yeah, the sample size calculation will definitely come into picture when we start the measure phase, because that's what we will be like from here on. After this, the measure phase is going to start, because this was the basic minimum requirement for us to know before we get into the measure phase. Now, just want to be sure, are we okay with this, everyone? Anyone has any questions? Again, we won't pick up a new topic here, but yes, just want to be sure, like if you anything that needs more clarity, that whatever we covered today, please do let me know.
One question here, Shashi. See,
Mhm,
when we were trying to do this mode, like
mhm,
when you have a discrete data,
mhm.
I'm just trying to see how we will be able to, what to say, um, get this confidence level and other things like,
For discrete data,
yeah.
no, for this, so for numerical data set, you can get confidence level. For discrete data, there will be a different, so when we talk about discrete, the concept will be different. Like when you have to look at sample size calculation, they say, if we go back to this, there are two, if we go to data files for class, which we will be covering it tomorrow, any which ways, the measure phase,
Mm-hmm.
here it says, see the two files, this sample size
Okay.
calculation for continuous data and sample size calculation for discrete data. The different
Okay.
formulas. So we will learn the manual way. We learn the, this is the formula for discrete. Remember this, this is, nobody would spare you in a job interview. When you're going for a Six Sigma job interview, uh, people will definitely ask you this formula because it has got cost implications. People do ask this formula. So we'll learn about the manual way. It's a very, this formula is very simple, and we'll do it on the Minitab also. But people do ask this question: how would you calculate the right sample size? Because if you don't know how to calculate the right sample size, you're going to mess up with the money, because every sample is a cost. So we'll learn about that. That's a simple one. But yeah, you got to keep this. Remember this thing. During job interviews, people do specifically ask certain questions, and this is one of the favorite questions which every recruiter has: sample size. So we must learn and understand when we like to. I'm sure we will be able to do that. But yes, important elements definitely. We will. By the way, I think like we must have filled in that form in case if somebody joined in late, then sort of a quick uh, reminder. We do have we have covered the define phase. We'll be supposed to sort of work on some questions. Some questions is what we have to uh, give me one quick second. I guess that's what I filled in. Okay. We've got this Excel sheet which is mock test details. Would request everyone to fill in this spreadsheet with your Gmail ID. I need a Gmail ID so that I can assign access to uh, this mock test drive. Like, so we have got a mock test which needs to be assigned, and that's what. So you can continue practicing this mock test, like a few, like, because define phase is over, you can finish your define phase mock test. As and when it gets over, every phase will get over, you'll get an access to this. So define phase questions you can attempt. So some questions, different types of questions. Similarly, the moment you're done with measure phase, you can try out measure, and so on and so forth. And for once we've done the base with the basic journey, another set of questions will get added to this, which is part, which will be something over and above these questions. So please do fill in sheet. It's there. So take your time, fill in. I will be picking up this tomorrow morning. I will assign anything because I'm sure it'll take some time. So when you're done with it, please just, I need to just, but it has to be a Google ID because that's what it works on. And I guess that should be fine. So do work on this. I'll just and fill it up, and that's where we'll have the sheets. So I just access assigned. So whenever a phase gets done, you can yourself do a self check whether, like, which area do probably I need more clarity on. Are we good with this, everyone, for today?
Yep.
All right. So I'll just place this Excel file right there where we have like the notes. So I'll remove the previous day notes and I'll put this file out there. So the notes section, same actually Google Drive where we placed this Excel notes. So I'll just quickly do that while we are on the call. So remove that previous one. So by the way, I'll be sharing some more additional data also. So the data we are dealing with, it's just to kind of get going, but we'll be sharing other data for you to work on, practice on as we get into the analyze phase, because then you need more of, because there are different types of data you will be dealing as a black belt. So yeah, we will more sample files which will come in. This is one which is already there. The other sample files which you should be exposed to. So we'll have a non-normal data that you will be working on. This one is normal data, but firstly you need to get hang of the normal data. Then we'll work on the non-normal also. So pretty much that should be taken care of. So I'm sure like by the time we get there, we'll understand that. Okay, I guess the sheet is uploaded. Yes, so you can have this updated sheet which is out there. And yes, let's connect tomorrow. Please do take good care of yourself, and let's connect tomorrow again at the same time.
Thank you.
Okay. Bye.
Thank you. Thank you. Take care.
Good night.
Good night. Good night. Bye-bye.
Thank you.
Thanks.
Bye.
Bye.